How many times in your career have you heard the phrase, "It works on my machine"? For decades, this simple sentence tormented developers and system administrators worldwide. An application would run perfectly on a developer's laptop, then mysteriously fail in production. Different operating systems, different library versions, different configurations. Each environment was a unique snowflake of potential failure. Before March 20th, 2013, deploying software was like trying to ship a fragile sculpture across the world without packaging. You'd carefully note every piece, every angle, every detail, then hope that whoever reassembled it at the destination got everything exactly right. Usually, they didn't. Today, we'll explore how a 5-minute presentation at a Python conference triggered a revolution that transformed not just technology, but the entire culture of how we build and deploy software. This is the story of Docker. But our story doesn't begin in 2013. It begins in 1979, in the halls of AT&T Bell Labs, where the Unix version 7 team introduced a deceptively simple command called chroot. This command, short for change root, allowed you to take a process and change its view of the file system. Suddenly, you could create a prison where a process could only see and access a specific directory tree. It was primitive, but it was the first step toward what we now call containerization. Think about the context. Computers in 1979 were massive, expensive machines shared by hundreds of users. Security wasn't just important, it was existential. If one user could access another's files, the entire system collapsed. Chroot provided that first layer of isolation, that first wall between processes. The 1990s brought evolution. FreeBSD, one of the most sophisticated Unix distributions of the era, faced a new challenge. Internet service providers needed to run hundreds of isolated customer environments on single servers. In 2000, Poul Henning Kamp, a Danish developer, introduced FreeBSD jails, the first true containers. Each jail had its own hostname, IP address, process space, and users. Processes inside a jail couldn't see outside it. It was complete isolation, yet incredibly lightweight. Yahoo ran thousands of jails across their infrastructure, proving the concept could scale. Then came Solaris. In 2005, Sun Microsystems released Solaris 10 with zones, their answer to enterprise containerization. This was FreeBSD jails taken to the next level, with enterprise features, cloning, live migration, resource management, and sophisticated monitoring. Financial institutions like Deutsche Bank ran thousands of zones, trusting them with mission-critical workloads. Solaris zones proved that containers weren't just clever hacks. They were production-ready technology for the most demanding environments. But Solaris was expensive, proprietary, and complicated. Meanwhile, Linux was growing explosively, driven by open-source culture and embraced by startups and tech companies. Linux needed its own solution, but the path forward would be more complex than anyone anticipated. Linux approached containerization differently, not as a single unified system, but as modular kernel features that could be combined. In 2006, Google engineers Paul Minaj and Rohit Seth contributed control groups, C groups, to the Linux kernel. Google had a unique problem. They managed thousands of servers running millions of processes, and they needed precise control over resource allocation. C groups allowed grouping processes and limiting their CPU, memory, disk I/O, and network usage. It was resource isolation built into the kernel itself. Simultaneously, Linux namespaces evolved. Starting in 2002, the kernel gradually added different types of namespaces, each isolating a different aspect of the system. Mount namespaces isolated file systems. PID namespaces isolated process IDs. Network namespaces isolated network stacks. UTS namespaces isolated host names. IPC namespaces isolated inter-process communication. User namespaces isolated user and group IDs. By the late 2000s, Linux had all the pieces needed for complete containerization. In 2008, these technologies finally came together in Linux Containers, LXC. It was powerful, sophisticated, and theoretically capable of everything Solaris zones could do. There was just one massive problem. It was extraordinarily difficult to use. Creating an LXC container required understanding namespace types, manually configuring C groups, setting up root file systems, configuring networking, and managing a maze of configuration files. Daniel Lescano, one of LXC's primary developers, later admitted that LXC was designed as a low-level API for experts, not a user-friendly tool for developers. The irony was painful. Linux had the technology for revolutionary containerization, but it was trapped behind a wall of complexity that only hardcore system administrators could scale. Enter DotCloud, a struggling startup founded in 2010 by Solomon Hykes, Sebastian Paul, and Kamel Funadi. They were building a platform as a service to compete with Heroku, trying to let developers deploy applications without managing infrastructure. They weren't winning. Heroku dominated the market, and DotCloud was running out of runway. But internally, DotCloud had developed something interesting. To isolate customer applications, they used LXC, but they'd built tooling on top that made it dramatically simpler. Solomon Hykes, as CTO, was particularly frustrated. He spent countless hours fighting dependency conflicts, version mismatches, and the infamous "works on my machine" problem. He started imagining, what if deploying software could be as simple as shipping a physical container? Same contents, same behavior, anywhere it goes. By late 2012, Hykes and his team started thinking their containerization tooling might be more valuable than their past business. They decided to take a risk, open source it, and see if anyone cared. March 20, 2013, PyCon, Santa Clara, California. Hykes took the stage for a lightning talk, 5 minutes maximum. He was nervous. He had one shot to communicate a vision he'd been obsessing over for months. His presentation, titled "The Future of Linux Containers," lasted exactly 4 minutes and 40 seconds. He started with a question that everyone in the room felt viscerally. How many of you have had problems with dependency hell, version conflicts, differences between development and production? Hands shot up across the auditorium. Then he showed Docker. Build an application, package it in a container, run it locally. Take that exact same container, run it on a remote server. Identical behavior, zero additional configuration, build, ship, run, any app, anywhere. The response was immediate. During his presentation, Docker's GitHub repository, created just hours earlier, started accumulating stars. By the end of the day, over 300 stars. Within a week, thousands of developers experimenting. The repository became one of the fastest-growing projects in GitHub's history. What made Docker different? 3 innovations. First, the Docker file. Infrastructure as code. A simple text file describing how to build a container, layer by layer, cacheable and reproducible. Second, Docker Hub, a registry for sharing container images, launched in June 2013. Suddenly, you didn't need to rebuild MySQL or Redis containers from scratch. You could pull them from a central repository in seconds. Third, and perhaps most important, radical simplification. Where LXC required arcane commands with dozens of parameters, Docker reduced container creation to Docker run. It wasn't just easier, it was a completely different philosophy. LXC treated containers as lightweight virtual machines. Docker treated them as enhanced processes. The months following PyCon were chaotic. Docker went viral in a way that surprised even its creators. Hacker News discussions hit the front page repeatedly. Reddit threads exploded. Twitter filled with developers sharing their Docker experiments. But Docker 0.1 was essentially a proof of concept. Buggy, incomplete, poorly documented. The team had to rapidly shift from building an internal tool to maintaining a project that thousands of people depended on. In July 2013, DotCloud announced a $10 million Series A, led by Benchmark Capital, specifically to develop Docker. Then in October 2013, they made a dramatic decision. DotCloud renamed itself Docker Inc. and abandoned the PaaS business entirely. They were betting everything on containers. Docker 0.6 arrived in September 2013, adding support for multiple architectures including ARM. But the real milestone came June 9, 2014, Docker 1.0, the first production-ready release. Docker Inc. launched commercial support, signaling that this wasn't just an open-source experiment. Companies could bet their businesses on it. The ecosystem exploded. Docker Compose emerged from an acquisition of Fig, allowing developers to define multi-container applications in simple YAML files. Docker Machine automated provisioning of Docker hosts across cloud providers, AWS, Azure, Google Cloud, DigitalOcean, with single commands. Docker Swarm provided native clustering and orchestration. These weren't just features, they completed a vision of making containerization accessible at every level of the stack. Strategic partnerships validated Docker's trajectory. Microsoft, undergoing transformation under Satya Nadella, announced Windows Server support. Google integrated Docker into Google Cloud Platform. Amazon launched EC2 Container Service. Even VMware, which could have seen containers as an existential threat to their virtualization business, embraced Docker and integrated it into vSphere. By 2015, Docker Hub surpassed 100 million image pulls. The GitHub repository became one of the platform's most popular projects. Industry surveys showed Docker had the fastest enterprise adoption rate of any technology in IT history. DockerCon 2014 attracted over 1,000 attendees, far exceeding expectations for a conference about a technology barely a year old. But growth brought challenges. As companies moved beyond development environments into production, they needed sophisticated orchestration, service discovery, health checking, rolling updates, secret management, network policies. Docker Swarm was simple and elegant, but some organizations needed more power and flexibility. That's when Kubernetes entered the picture. In June 2014, while Docker was celebrating its 1.0 release, Google quietly open-sourced a project called Kubernetes. Based on Borg, Google's internal system for managing billions of containers across their data centers, Kubernetes represented a decade of hard-won lessons about running distributed systems at planetary scale. Initially, Kubernetes seemed complementary to Docker. It used Docker as its container runtime and focused on orchestration, while Docker focused on developer experience. But philosophical differences quickly emerged. Docker Swarm prioritized simplicity. You could create a production cluster with a few commands and deploy using the same Docker files you used in development. Kubernetes embraced complexity in pursuit of power. It introduced concepts like pods, services, deployments, config maps, secrets, and ingresses, each with its own API and YAML specification. The learning curve was steep, but the capabilities were extraordinary. Between 2015 and 2017, what the industry called the orchestration wars played out. Docker Inc. pushed Swarm, emphasizing ease of use. Google championed Kubernetes, emphasizing flexibility and power. Apache Mesos, HashiCorp Nomad, and Rancher competed for niches. But gradually, the industry converged toward Kubernetes. Google launched Google Kubernetes Engine. Amazon, despite having built its own container service, launched EKS for Kubernetes. Microsoft followed with AKS. The message was clear. Kubernetes was becoming the standard. Docker Inc. read the writing on the wall. In 2017, they made a strategic pivot. Docker for Mac and Docker for Windows integrated Kubernetes as a first-class orchestration option. Docker Enterprise embraced Kubernetes. Rather than fighting the trend, Docker focused on what it did best: developer experience. But standardization required more than just market convergence. In June 2015, the Linux Foundation launched the Open Container Initiative with Docker Inc. as a founding member, alongside CoreOS, Google, IBM, Microsoft, and Red Hat. The OCI created two critical specifications: the runtime specification, defining how to execute a container, and the image specification, defining container image formats. These standards ensured that containers created with different tools could run on different runtimes. It separated the concept of container from any particular implementation. In 2017, Docker Inc. donated Containered, the runtime it had been developing internally, to the Cloud Native Computing Foundation. Containered became an independent project, used not just by Docker, but by Kubernetes and other orchestrators. This separation of runtime from tooling was strategic. It allowed Docker to focus on developer tools while the community innovated on orchestration. The symbolically defining moment came in December 2020. Kubernetes announced it would deprecate Docker as a container runtime in favor of more specialized runtimes like Containerd and CRIO. This caused confusion. Many thought Docker containers would stop working on Kubernetes. In reality, containers built with Docker continued working perfectly. They just ran via Containered instead of Docker Engine. But symbolically, It marked the end of an era where Docker and container were synonymous. While we focused on technology, Docker's most profound impact was cultural. It didn't just change how we deploy software, it changed how we think about software. Docker ended, it works on my machine, permanently. A container that worked on a developer's MacBook worked identically in production. This wasn't just about reducing bugs, it fundamentally changed the relationship between development and operations. The DevOps movement had preached integration between these traditionally siloed teams, but lacked practical tools. Docker provided the missing link. Developers packaged applications with all dependencies. Operations deployed those packages without understanding internal details. The friction that had plagued software delivery for decades simply dissolved. This enabled the microservices explosion. Microservices architecture existed before Docker, but Docker made it practical. Before containers, deploying hundreds of separate services was a management nightmare. After Docker, each service lived in its own container with isolated dependencies. Orchestration tools managed them as components of a unified system. Companies like Netflix decomposed monoliths into thousands of microservices, achieving unprecedented scalability. Uber rebuilt its entire architecture on containers. Airbnb containerized everything. Docker democratized the cloud. Before containers, cloud deployment required significant infrastructure expertise. A three-person startup couldn't compete with enterprises that had entire IT departments. Docker changed this. That three-person startup could now package their application in a container and deploy it to AWS, Azure, or Google Cloud in minutes. The playing field leveled. Innovation accelerated. The numbers tell the story. Docker Hub grew from 1 billion pulls in 2015 to over 100 billion annually today. A 2019 Stack Overflow survey showed 83.8% developer satisfaction, the highest of any platform. By 2020, 83% of companies used containers in production. The container market grew from zero in 2013 to over $8 billion in 2020, projected to reach $15 billion by 2025. According to Red Hat, 95% of Fortune 100 companies now run containers in production. This isn't gradual adoption, it's complete transformation. Consider 3 real-world examples. Netflix manages over 3 million container instances serving 200 million subscribers, with Adrian Cockcroft crediting Docker for enabling global scale with small teams. Goldman Sachs built Symphony, a Docker-based platform that reduced application deployment time from months to days while cutting operational costs 50% and increasing hardware utilization 300%, all while maintaining financial sector compliance. General Electric deployed Docker containers to thousands of edge devices in harsh industrial environments, running the same analytics code on wind turbines in the North Sea that they developed in cloud data centers. Success brought challenges. Security emerged as the primary concern. Containers share the host kernel. A kernel vulnerability can compromise everything. In 2019, Sysdig found 58% of Docker Hub images contained known vulnerabilities. Many ran processes as root or included unnecessary software, expanding attack surfaces. The industry responded with vulnerability scanners, distroless images containing only essential components, and more secure runtimes. But security remains an ongoing battle. Docker also introduced new complexity. While it simplified deployment, scaling to thousands of containers demanded expertise in cluster management, inter-container networking, storage persistence, and service discovery. Many companies discovered that starting with Docker was easy. Operating it at scale required significant investment in tooling, monitoring, and specialized knowledge. Paradoxically, Docker, created to solve portability problems, created new lock-in. Companies built Docker-specific workflows and tooling, making migration to alternatives difficult. The ecosystem fragmented: Docker, Podman, Containered, CRIO, each with different trade-offs and capabilities. As we approach 2025, the ecosystem continues evolving. Security is shifting towards zero-trust models, where every communication and resource access is verified rather than assumed. Tools like Istio, Service Mesh, Falco Runtime Security, and Open Policy Agent enable granular policies and continuous monitoring. WebAssembly is emerging as an alternative for specific use cases, promising universal portability and superior performance for certain workloads. Docker Inc. itself now supports WASM, recognizing the future may include multiple paradigms. Sustainability has become a priority. Projects like KubeGreen automate scaling down non-critical workloads to reduce energy consumption. Optimized images reduce startup times and bandwidth usage. Meanwhile, containers are spreading to the edge. Projects like K3s bring Kubernetes to resource-constrained IoT devices, extending containerization from data centers to wind turbines, oil rigs, and manufacturing plants. Alternative tools have emerged. Podman, from Red Hat, offers daemonless operation and rootless containers, solving security concerns while maintaining Docker CLI compatibility. Builda and Scopio provide specialized tools for image building and management. The ecosystem has matured from a single solution to a diverse toolkit. Looking forward, several trends are reshaping the container landscape. Artificial intelligence is transforming container management. Systems now automatically optimize resource allocation, predict failures, and tune performance in real time. Kubernetes is integrating AI-native features, from intelligent autoscaling to predictive scaling based on machine learning models. Quantum computing, while still experimental, may require entirely new containerization paradigms. How do we isolate quantum workloads? How do we manage shared quantum resources? These questions seem distant, but are already being explored in research labs. Computational biology and DNA storage represent another frontier. As we begin using biological systems for computation and storage, the concept of container may evolve to encompass biological computational resources, extending the abstraction into entirely new domains. But perhaps the most important evolution is cultural. Docker demonstrated that developer tools can change the world. Before Docker, infrastructure software was dominated by expensive, complex enterprise products. Docker proved that open source, community-driven, developer-friendly solutions could not only compete, but dominate. This lesson spread throughout the industry. Today, we see open source projects leading in databases, messaging, monitoring, networking, and countless other domains. Docker also taught us that simplicity is sophistication. In an industry obsessed with technical complexity, Docker reminded us that the best solution often isn't the most technically advanced. It's the one that solves a real problem in the simplest possible way. LXC was technically capable of everything Docker did, but Docker won because it was simple enough for any developer to use. The mental models Docker introduced, infrastructure as code, immutable deployments, cattle not pets, have spread far beyond containers. We now apply these concepts to databases, networks, and entire cloud environments. The philosophy outlasted the specific implementation. In 2018, Solomon Hykes left Docker Inc. to found Dagger, a new startup focused on CI/CD. In his farewell letter, he wrote, "Docker has shown that developer tools can change the world. Our work isn't finished, it's just begun." That statement captures Docker's essential legacy. When Hykes stepped onto that PyCon stage in March 2013, he probably didn't imagine that his 5-minute presentation would trigger a revolution still unfolding today. But maybe that's the point. The most important technological revolutions don't come from massive corporations with enormous budgets. They come from individuals who see a real problem and solve it in the simplest way possible. Docker taught us that in technology, simplicity is sophistication, that bottom-up adoption can be more powerful than top-down mandates, that open standards will always triumph over walled gardens. That developer experience isn't a luxury, it's fundamental. As we look toward WebAssembly, quantum computing, and paradigms we can't yet imagine, we carry these lessons forward. The next revolution probably won't come from whoever builds the most complex technology. It will come from whoever makes something impossibly complicated beautifully simple. Docker didn't invent containers, but it made them accessible to everyone. And in doing so, it changed not just how we deploy software, but how we think about software itself. That transformation, from complexity to simplicity, from expert tools to universal adoption, from technology to culture, is Docker's enduring legacy.